Hello. Let's discuss about superscalar architecture and fundamentals. Coming to the definition, superscalar architecture is an advanced microprocessor design that allows the execution of multiple instructions per clock cycle by using multiple execution units. Unlike scalar processors, which execute only one instruction per cycle, superscalar processors improve performance by exploiting instruction level parallelism, often known as ILP. So, this architecture is used in modern high performance CPUs, including those from Intel, AMD, and ARM. It allows programs to run faster without increasing clock speeds significantly. Let's discuss about some key concepts in superscalar architecture. So coming to instruction level parallelism, as I already mentioned, ILP, it refers to the ability to execute multiple independent instructions simultaneously. So these processors analyze instructions and execute them in parallel whenever possible. Multiple execution units, as again mentioned in the definition, a superscalar CPU includes multiple execution units like ALUs, FPUs, load store units, etc., enabling it to process more than one instruction per cycle. So different execution units can handle integer, arithmetic, floating point operations, and memory access and branch instructions separately. Third point, instruction fetching and decoding. The CPU fetches multiple instructions at once, so often using prefetching mechanisms. So decoding involves identifying dependencies between instructions and scheduling them efficiently. The fourth important point is dynamic scheduling and out-of-order execution. So modern superscalar processors use dynamic scheduling, example, Tomasulo's algorithm, to rearrange instructions dynamically for a better efficiency in execution. So this allows a processor to execute instructions as soon as resource becomes available, rather than strictly following the order in which the instructions were in execution. Coming to the next important point, the register renaming. So this helps eliminate false dependencies like WAR, WAW, and read after write. So okay, WAR is write after read, WAW is write after write, and RAW is read after write. So these are anomalies which we'll be discussing later. So by providing unique registers for different instructions, it helps eliminate these false dependencies. Another important characteristic of this processor is branch prediction. So superscalar processors use branch prediction to anticipate control flow changes, so reducing delays caused by all these conditional branches. Mispredictions, however, can lead to pipeline flushes, reducing efficiency at some cases. Coming to the next point, execution pipelines. So execution pipeline is each execution unit operates in a pipeline fashion, allowing different stages of multiple instructions to be processed simultaneously. For example, when one instruction is being executed, another can be decoded while the third one can be fetched. Commitment and retirement is another thing of superscalar processors. So instructions are committed in order to maintain program correctness. Even though execution is out of order, the final results must appear in expected order. Coming to a simple diagram of the architecture for the superscalar processor. So this is how it looks when multiple processors can still accommodate using the multiple execution units for fetch, code, decode, and all that. So superscalar architecture allows them to run multiple instructions in a single clock cycle, improving performance and efficiency. So if we compare this with a conventional scalar architecture, let's draw down to a simple table where it is clearly mentioned, as I already discussed, the instruction execution is one instruction per cycle for an ordinary processor, while a superscalar processor can run multiple instructions per cycle because of its multiple execution units. So that's what is mentioned as parallelism. That's parallel instructions executed at the same time. So it is low in terms of scalar processor because it's one or highly maximum possible of two instructions maybe at some times, while superscalar processors can have multiple executions at a time. Coming to examples, scalar processors, which we are very much aware of, the Intel 8086 and such microprocessors, while all our laptops and mobile phones, the processors inside, the Intel cores, AMD Ryzen's, and Snapdragon, all those modern processors are superscalar processors. So scalar processors execute only one instruction per cycle, while your superscalar processors have multiple instructions executed per cycle. So, in terms of result, superscalar processors have a very higher throughput and better performance when compared to scalar architectures. Coming to the next point, so discussing about throughput. Throughput is basically the number of instructions executed per cycle. So, as I already mentioned, superscalar processors have the capacity to run multiple instructions per cycle. So the throughput is going to be high, which is basically the efficiency going to be high. So that's what is mentioned here. So superscalar CPUs increase the throughput by executing multiple instructions in parallel. For example, it's a, say you have a two instruction super processor. So when instruction one and instruction two, both of them are there, they can run at the same time simultaneously because of having the multiple execution units. When instruction one is doing fetch, maybe instruction two is on hold, but once it reaches decode, instruction two comes to fetch. So parallelly things happen and produces a better efficiency when compared to the scalar processors. Coming to some hazards for super processors, instruction dependencies and hazards. This was mentioned initially in the first characteristics as well. So that is read after write, the true dependency. It's called true dependency. This is a condition when an instruction needs data from a previous one, but the result isn't ready yet. And then we have read after read, write after read, which is called anti-dependency. So this is a later instruction writes to a register before an earlier instruction reads it. These are anomalies which are possible when multiple instructions run parallelly. Write after write is another one anomaly or hazard called as output dependency. So here it's a scenario when two instructions write to the same register and the order matters. So there could be, instruction one and instruction two, when there are two instructions executing, writing something. So when instruction one writes and then instruction two writes, or if instruction two writes first and instruction one writes later, the order will change. Then there is anomalies and hazards possible in your expected outputs and the execution. So the other type of hazard is structural hazard. So by the name, it is basically lack of hardware resource or when there is limit. This is on a practical note on a real processor when multiple instructions need the same resource at the same time, which is not possible. So this leads to a structural hazard. Okay, coming to the next hazard, it is control hazards. So control hazards are when processor guesses wrong in branch prediction. Like this was also mentioned in the characteristics initially. The branching is also branching prediction is another feature of superscalar processor, but sometimes, like mentioned, it could cause some wrongly predicted values, which could result in fact, even in a higher execution time. So let's discuss about that here. Yeah. So when the processor guesses wrong in wrong predictions, so in that case, the execution might go wrong. So basically, then it has to discard them, and then again it should take back and start executing from the first. So these are some dependencies and hazards for a superscalar processor. But these things can still be reduced and have an efficient superscalar by following some techniques, some basic techniques to improve the performance. Coming to the first one, say out of order execution. So this is executing instructions as resource becomes available, only when resources are available. So in traditional pipelining, instructions execute sequentially, meaning you'll have a lot of stalls. That is data, I mean, the instructions waiting for resources or anything else like that for IO operations maybe. So this out of order execution is a technique which can be followed that reorders instructions dynamically to keep the pipeline full, so reducing the execution time. So here the CPU basically decouples instructions like fetch and execution and allowing independent instructions to execute as soon as the resource is available. So even if earlier instructions are stalled, this will move the instruction which is in the latter to the forward as its respective resources which it requires are available. So this is handled by a special buffer called as reorder buffer that ensures the proper order, the program order is proper and there is no anomalies like that. Coming to the second technique, that is branch prediction, which was already discussed before. So it can be made better by reducing stalls and from also control hazards. So this control hazard occurs when the CPU doesn't know which way a branch will go. Without prediction, the CPU must wait until the branch outcome is known, leading to stalls. So until it predicts, it checks, goes through all the branches, the CPU will have to wait, which is going to cost a lot of time. So for this, the CPU uses the prediction that which branch will give the desired outcome before execution. So if the prediction is right, then there is no stall. But if it's incorrect, then the CPU will flush that wrong instruction and re-execute the correct ones. So by checking it. So branch prediction also has sub different types like static prediction, dynamic prediction, and tournament prediction. So static prediction assumes backward branches, while forward branches are not taken. Dynamic prediction uses branch history table, which is the special table which is used in prediction technique for a superscalar processor. This tracks the past decisions and predicts future outcomes. The tournament prediction is another type of combined multiple prediction strategy, which definitely results in a higher accuracy, more or like a hybrid prediction system. Okay. So discussing about superscalar versus super pipeline architectures, this will be carried out by my teammate from now. Thank you.
Now, thank you, Naveen. Let's discuss the differences between superscalar and superpipeline architecture. A superscalar processor has multiple execution units, allowing it to fetch, decode, and execute multiple instructions in a single clock cycle. It focuses on instruction level parallelism by executing independent instructions in parallel. On the other hand, a super pipeline processor splits the pipeline into more stages so that each stage does less work per cycle. This allows the processor to start a new instruction every shorter clock interval. We could simplify that a superscale architecture has multiple instructions per cycle, but a super pipeline has one instruction per cycle, but every cycle is faster. Now, superscale architecture. It executes multiple instructions per clock cycle, whereas super pipeline executes one instruction per clock cycle. Superscalar has multiple execution units, whereas super pipelines has more pipeline stages to break down the execution. Superscalar exploits instruction level parallelism, whereas super pipelines increases the pipeline depth for higher clock rates. Superscalar needs complex control for parallelism, whereas super pipeline is simpler. Superscalar can issue two or more instructions per cycle, whereas super pipeline has only one instruction per cycle. Superscalar depends on how low a data control dependencies. Super pipeline needs careful design for balanced stage delays. Superscalar needs advanced logic for hazard detection and scheduling, whereas super pipelines has hazards, but it's in pipeline status. Superscalar is more common in modern GPU CPUs, but super pipelines were used in early RISC designs. Superscalars require more hardware units as it's using more CPUs, more execution units, whereas super pipelines does not use higher units, but it has higher control logic. Example of superscalar is Intel Core and AMD Ryzen. For super pipeline, it's MIPS R4000 and early designs of AMD. Now, here is a basic understanding of what happens. So up above here, it's a diagram of base machines where on the x-axis it's time in cycles and the y-axis it's successive instructions. So like how many what instruction is going on. In the base machine, as you can see, that there is one instruction. After the completion of the first instruction, the second instruction starts. So it is so the design is such that it does not allow multiple instructions to go at once. Whereas in super pipeline, you can see that multiple instructions have been started, but the execution is not fully complete. Like when the execution of first block is half complete, this execution of second block is initiated, and it goes on for it. So it takes lesser clock cycle than the base machine. So it is better. But in superscalar, two of the execution units of different instructions are being executed at the same clock cycle as here, here, and here. So it takes even less time than the super pipeline. So now let's see one example. So here is an example for two-way superscalar execution of instructions. So these are the instruction set. So at first it's load R1 at the rate 1000. So like it will load the value add 1000 there to R1. And then same for R2, it will load the value at 1008 and add R1, comma 1004. So it will add the value of R1 with 1004 and then store it in R1 and add R2 at the rate 1000C. So it will take the value at 1000C, add it to R2. And then finally it's add R1, comma R2. So it will add the both values of R1 and R2 and store it in R1 and store R1, comma 2000. So like it will take the value of R1 and store it at 2000 value. So now here is the instruction cycle. See, the load R1 and R2 are both executed parallelly. Like the instruction fetch, instruction decode, and operand fetch is done parallelly as they are two independent executions. They do not depend on each other. So we could just execute them without any issues. And same goes for this add R1 and add R2. These instructions are independent of each other. They do not depend on any of the other instructions but output. So like at the first instruction cycle, both starts as instruction fetch, instruction decode, operand fetch, and then executes. So both executes at the same time. But for this add and store, these two cannot be run parallelly. Cannot be run parallelly as store R1 requires the value of R1, which is being updated at the R1, add R1, comma R2. So we will start it. We will start the add R1, comma R2 as instruction fetch on the second instruction cycle. Then we'll decode it and then we'll execute it. And then we'll start the instruction fetch of the store command, store, and then instruction decode. And then we will wait till the execution of add R1, R2 is completed. And then we will write it to buffer. So this is how the instructions are executed parallelly in a superscalar processor. Thanks.